Addition and multiplication operations on equivalence classes. We define addition and multiplication on equivalence classes. Then, we show that the addition of equivalence class is well defined, meaning the class A, B has another representation, A prime, B prime, and the class C, D has another representation, C prime, D prime. Then the sum of the two classes A, B, and C, D is equal to the sum of the classes A prime, B prime, and C prime, D prime. This means the sum of two equivalence classes is independent of the representation of the classes. If the sum of two equivalence classes is different from the sum of the equivalence classes represented by different members of the respective classes, then the addition is not well defined. Next is the definition of the product of two equivalence classes. Here also, we show that the product of two equivalence classes is well defined. Class A has representation by any of its members, and Class B has representation by any of its members. Then the product of Class A and Class B does not change its value depending on the representations. The product of two classes is attributed only to the classes, not to the individual members. So the multiplication of two equivalence classes is well defined. Each class will represent a unique integer. Conversely, an integer will correspond to a unique class. One can see that for a given class A, represented by A, B, then a minus B is the unique integer. An interesting fact is that in these operations, addition and multiplication, we use only the known arithmetic properties on the set of natural numbers, namely, commutativity and associativity of addition, cancellation law of addition. Likewise, we use only commutativity, associativity of multiplication of natural numbers, distribution of multiplication over addition of natural numbers, and the cancellation law of multiplication of natural numbers. The goal of extending these arithmetic properties to the set of integers is achieved through the equivalence class. It is straightforward to prove these properties on the equivalence classes with our definitions of addition and multiplication, as they are well defined. Algebraic properties of the set of integers, Z. The collection of equivalence classes A, B with AB from the set of natural numbers is called the set of integers. It holds the commutative property of addition. It holds the associative property of addition. The addition of integer 0 to any integer is the integer itself. The 0 integer is unique, and it is called the identity element of addition. It is similar to the first condition of the definition of the addition of natural numbers. For each integer, there exists a unique integer called the inverse element of the integer. This property is not in the set of natural numbers. Subtraction is defined in the set of integers. Likewise, the cancellation law of addition of natural numbers, the cancellation law holds in the set of integers too. Multiplication properties of the set of integers. The commutative property of multiplication holds in integers, as in the case of natural numbers. The associative property of the multiplication of integers is there, similar to the natural number. Then we have the identity element of multiplication of integers. It is also similar to the first condition of definition of multiplication of natural numbers. Multiplication of any integer by the multiplicative identity element is the integer itself. The cancellation law of multiplication of integers holds true like in the case of the set of natural numbers. The distributive law of multiplication over addition. This law holds true in the case of integers. The proofs or verification are straightforward, using the definition of equivalence classes, addition, and multiplications. Next is the order properties of integers. First, we define order in integers, similar to n. Order in integer is transitive, as in the case of the set of natural numbers. Next, the addition of integers preserves the order in the set of integers, similar to the case in the set of natural numbers. Then comes the preservation of order by multiplication of positive integers, similar to n. Unlike in the case of natural numbers, multiplication of integers by negative integers reverse order. This is also a distinctive property of integer different from the set of natural numbers. Embedding of n into z via the embedding map. First, we show that the embedding map is independent of the choice of integer a. This means that the natural number k corresponds to a unique equivalence class or integer. The value of f of k does not depend on the individual member of the class. It gives the class or the integer, so it is well defined. It means f is a function from n into z, the set of integers. Let us illustrate some of the values of the function. F of 0 is equal to class a plus 0, a, which is the 0 integer, or the additive identity. F of 1 is equal to class a plus 1, a, which is the integer 1, or the multiplicative identity. F of 2 is equal to class a plus 2, a, which is the integer 2, and so on. From the example, intuitively, although we will prove it later on, it seems that f maps n into the positive integers. If f is 1 to 1, f preserves the addition, that is, f maps the sum of two natural numbers into the sum of the corresponding integers or classes, and f preserves the multiplication, that is, f maps the product of two natural numbers into the product of the corresponding integers or classes. Then we say that f is an embedding map, and n is embedded into z. It means that the set of natural numbers is equivalent to a subset of integers by preserving the addition and multiplication operations. So instead of using the cumbersome notation of integers by equivalence classes, that subset of integers can be denoted by the set of natural numbers itself. Because notation can be done with many symbols, the idea is the preservation of the arithmetic operations, addition, and multiplication. Also, the set of integers is constructed from the set of natural numbers. So it is quite natural to say that n is a subset of z. Somehow, if we can show that, this embedding is the set of non-negative integers, which we will do later, then the remaining set of integers is the set of negative integers. F of ab equals f of a dot f of b means f preserves multiplication. That is, f preserves the algebraic structure of multiplication in n into z. So f of n, a subset of z, can be replaced by the notation n itself. Therefore, the set of natural numbers is a subset of the set of integers. This is the meaning of the embedding of n in z. When we see the natural numbers 0 and 1 from the point of view of 1, one step ahead of 0 is 1, the never-ending moving forward, a characteristic property of n. But if you see from the point of view of 1 towards 0 or moving backward, the concept of a negative number comes up. So is the set of integers. Positivity in Z via equivalence classes. An integer a is said to be positive if it is greater than 0. It is said to be negative if it is less than 0. Theorem. An integer. A equals class A. B is positive if and only if A is greater than B. The proof is straightforward from the definition of order. It is a very simple result, but it says that an integer is either positive or 0 or negative. Because of the law of trichotomy of natural numbers, either A is greater than B or equal to B or less than B. So the set of integers is precisely the disjoint union of positive integers, negative integers, and the 0 integer. When we see the class 5, 3, moving from 3 toward 5, we reach there by taking 2 units in the forward direction, so it represents the positive integer 2. But for the class 3, 5, from 5, we move backward by 2 units to reach 3, so it represents negative integer 2. The next theorem, together with the embedding theorem, says that the set of natural numbers, which is a subset of z, is precisely the non-negative integers, that is, the positive integers and the 0 integer. Then, what about the negative integers? It is an interesting question. The next theorem gives the answer. The negative integers are precisely the additive inverse elements of the set of positive integers. If a is a positive integer, then its inverse element minus a is a negative integer. Conversely, if a is a negative integer, then its inverse element minus a is a positive integer. Hence, a is a positive integer if and only if minus a is a negative integer. So, z is precisely the set of non-zero natural numbers, called positive integers, their inverse elements, called negative integers, and the additive identity element or the zero integer.